6 of your textbook, and that's motion in a circle. So, well, basically, we discuss in this the kinematics of our circular motion, uniform circular motion. We will talk about centripetal accelerations, we'll talk about centripetal forces, and it's more focused only towards you have something that is moving in a circle, and what's keeping this ball, or you can say a particle, what's keeping it in this motion? It's what's keeping it in moving in a circle. So we'll need some quantities, we'll need some things to study this kind of kinematics. And so we'll start with something that is called the angular displacement. And angular displacement, we'll use the appropriate units to represent angular displacement or angles, is radians. Now, radians is just an SI unit for your measuring angle. And so suppose if your angle is theta, then you can also relate, there should always be, if you're, so for example, let me give you an example. If you're using kilograms and grams, so there is always a relation from going from kilograms to grams and then from grams to kilograms. Similarly, if you're using the radians unit for angle, then you should be able to relate it to the degrees unit for the angle. And it's done so by that in one complete revolution, an object rotates through 360 degrees or 2 pi radians, which just means that pi radians, it's pi rad, is equal to 180 degrees, right? So, okay, can you tell me if there is, you have this thing where it says this much time is left for the meeting?
Not yet.
You cannot see the time of meeting? How much time is left? Okay.
Already 25 minutes gone. That means around 15 minutes left.
Right. Okay. So, right. So we have pi radians is 180 degrees. So that's the relationship between radians and degrees. So we have that when an object is moving in an angle with respect to the center of the rotation, the angle theta is known as the angular displacement. So what that means is you have, so something is bound to this center point, right? And it's moving about this center, so it will move like this. So suppose that this is your reference line, and you measure the angle from this reference line. So whatever distance that this moves in this direction, right, you can measure the angle from this reference line, and that would be the angular displacement of this ball that is moving. So let's call it a ball, or let's call it a particle, whatever, right? So that's your angular displacement. That's how an angular displacement is defined. So if I have something that's defined as angular displacement, then I can define what is called the angular velocity. So it is how fast does your displacement changes, the angular displacement. How fast does the angular displacement changes is called the angular velocity, omega. And it's represented with omega, where you can mathematically write it as the ratio of your angular displacement to time. Now, if you have a one complete revolution, which just means that suppose it starts from this point A and it moves in a circle and it comes back to this point A, then that's one complete revolution. And for that, the angular velocity is defined as 2 pi over t, where t is the time period. And the fact that we have this time period over here, it comes from this thing that time period is basically defined as the time it takes for your body to complete one complete revolution, which was defined over here, right? So starting from one point and coming back to that point in a circle is defined as a complete revolution. Right. So next we have a linear velocity. Now, what is linear velocity? If you have something that is moving in a circle, so something is keeping this particle moving in a circle. So let's just try to draw it over here. And suppose at this point, suppose that there is some string that is attached to this ball or a particle, and it's keeping it moving in a circle. What if this string goes away? The string vanishes. What would happen at that point? Suppose that it was moving in this direction. Can you tell me what would happen if I just remove the string, or someone just cuts the string off? What would happen to this particle?
It will no longer move in a circular motion.
Yeah, but what would be its behavior then? As soon as I cut this, where does this particle go? Will it fall back to the ground or what? Anything you can say, even if your answer is wrong. Nobody's judging you here, right? Nobody's judging anyone here. If your answer is wrong, you'll learn something. You might have the correct answer in your head and you're just not saying it. So just say whatever is in your mind. What do you think would happen to this ball?
It would go
Like I
flying,
said, it would go
flying away.
Yeah, exactly. So it would go flying. So it would go in this direction, and this let me just draw it properly. So it would, if it were moving like this in this direction, right? If it were moving like this, then the tangential component is this thing, right? So it would go straight in this direction. So now if it were at this point and then the string was cut, then the string was cut, and again we know that it's moving anti-clockwise. So what would happen? It would go flying in this direction if I cut the string off. So with which velocity does it go flying in this direction is known as the linear velocity, and it's represented with v. So that's the linear velocity. And it is also, you can use the word instantaneous velocity at any point on this circle, because as soon as you cut that string off, with that particular velocity, it would go flying off in the direction corresponding to the which direction it was already moving in the angular velocity. So is this thing clear? Is the linear velocity, do you understand what linear velocity is? Or is there any question?
No, sir.
Right, okay. So linear velocity, it is defined mathematically as the arc length over time that it takes to move to that point, right? So we have this thing, we have v, linear velocity. It is defined as, why am I writing it down? It's mentioned over here already. So it's the arc length, and we know from from mathematics that arc length is simply r times theta. Do you have any problem in understanding what arc length is, or do you know what an arc length is? It's just So suppose you have this angle theta over here, and this is the arc that it forms. And so the length of this region is the arc length. And you can find that by simply multiplying this length with the angle theta. And so if this length is r, then you have r times theta is the length of this arc. Right? So what happens, why is it arc length over time taken? The reason for that is because if it was moving in some direction, right? So what you do is, suppose it's at this point, and initially just before that it was at this point. So what happened is, it would have the velocity that it would have had between these 2 points, this region. So what you do is, the time it takes for this particle to move from here to here, where you just cut this string off, is the time taken, and the length of this path was the arc length of this circle, which is r theta. So that gives you r theta over t, which is basically r times omega. And the reason for that is because theta over t was defined as omega, where omega is the angular velocity. So you can even write, so you can write down your linear velocity in terms of your angular velocity, which you should not be surprised. It should have been possible because it was already related. The linear velocity was related to the angular velocity.
Sir, can you explain it again?
Yeah, of course I can. Which part are you talking about?
Sir, the formula.
Oh, right. So why is it like this? Well, so you have to imagine, right? So suppose that you have some string attached to a particle or a ball, and you're moving it in a circle. When you break the string, what happens is, you have to consider this, some change in angle, change in theta. You have to consider some infinitesimal, you can say infinitesimal area or infinitesimal length, which means that very small. So what was happening just before I cut the string, and right at the moment I cut the string? So that's this length over here, which is your arc length basically. And the length of this string is basically the radius of the circle that when you are moving your string or the object in a circle. That's r. And the angular displacement just before and right at the moment when you cut the string is this theta. So this gives you this length, which is r times theta. And I want to find the velocity of how fast did this point move to this point. So this point, how fast did this point move to that point? So I'll just take this length that it covered divided by the time that it took to cover that length. So that is this linear velocity. Is it any better now?
Yes, sir.
Okay, right, perfect. Perfect. So I got this notification a couple of minutes ago that this meeting will end in 10 minutes apparently. Okay, do you see the time that is remaining?
Yes, 2 minutes and 54 seconds.
Right. So yeah, so we have around 3 minutes left. So okay, so is there any question from whatever we have discussed so far?
No
Right.
questions.
Okay. Okay. So So now I've already explained this thing to you, that the direction of the linear velocity is tangent to the circle, right? You can see that because when I drew this thing, so this was just a tangent at this point where the object was. This line was a tangent to that point, and this tangent vector is defined as the linear velocity of this object at that particular point. And because it's defined using this tangential vector, it's also referred to as a tangential velocity, right? So these terms, they're just the same thing, right? Tangential velocity and linear velocity is exactly the same thing. Okay, so right. Now, if you look, even if you look at this expression for omega, which is angular velocity, and for v, which is the linear velocity, you can immediately tell that this thing omega, the angular velocity, at every point on your circle would remain constant, right? So if it was moving in this, if it was at this point at some time, or if this ball was at this point at some time, the angular velocity remains constant, right? You can look at this expression and you can tell that. But what if I consider the linear velocity? Now, linear velocity is clearly, if I have points that are away from this axis, this line. So, for example, the length of the string gets larger, right? What happens then? Then I cannot draw it properly over here, but this is still moving in a circle, and the length of the string is now some r prime. What happens then? The tangential velocity would increase, and you can see that from this expression, because the tangential velocity is proportional to the radius r. So if I increase the length of my string, then the linear velocity would increase. So what is happening is that if I use a longer